So after understanding the difference between scalars and vectors, it's time for segment 3, which is about representation of vectors. So please enjoy. So now the most important part, which is called the representation of vectors. Now to have the representation of vectors, we need to focus on two things. Firstly, the magnitude of the vector, and secondly is the direction of the vector. So first let us focus on the magnitude of the vectors. So any vector of any length will be represented by a letter with a arrowhead in the top. It can be letter A, it can be letter B, C, or anything like that. Even small letters can be also used to represent a vector. It can be also written in this way. Okay, it can be a C vector like this. Okay, something like that. Now this is how a symbol of a vector is written. Now the magnitude of this vector will be represented by this symbol with a modulus sign. Okay, so if a vector is having a modulus sign, that means it represents the magnitude or the length of that vector, or simply the letter represents also the magnitude or the length of the vector. The second thing is the direction. Now the direction of a vector can be represented in 4 different ways. So let's see what are the ways in which the direction can be represented. So defining the direction of a vector, the first way is using the language. Okay, we can simply explain the direction in which the vector is pointed. For example, a train is moving with a velocity of 10 meters per second due east, which clearly defines the velocity is in the direction of east. The second type of way in which we can define the direction is graphically by using a directed line segment. So if we have already told that if this is the directed line segment, the angle that it makes with x-axis, or it may be with y-axis or z, any axis, the angle it makes defines the direction of that vector. The third way is basically in terms of any other fixed direction. Say if I am walking on the road, it will be basically parallel to the road. I can say if I am climbing on the stairs, then I can say if the stair is inclined, say at an angle of 45 degree, I can say I am moving at an angle of 45 degree with respect to the horizontal. So the horizontal is the basic thing, the base with respect to which we basically measure the angle. So if we have some definite direction, fixed direction, with respect to that we can define the angle, like a force of 10 Newton applied at an angle of 30 degree with respect to the horizontal direction. So the diagram will be like this. If we have this as the floor, okay, and a force is applied at an angle of 30 degree with respect to the horizontal. So the force can be pull or push, both. Let us say the force is a pull force. Okay, it is at an angle of 30 degree with respect to the horizontal. So this is the force F, which is a vector, and this angle here is 30 degree. Okay, that is how the situation is. Now the fourth one, which is the most important one, is algebraically by using unit orthogonal vectors. Unit orthogonal vectors are massive things. Just with some symbols we can explain the magnitude and the direction both. Okay, this is a unique way of representing a vector. Now this is explained in great depth in the next slides. So let's proceed. So before getting into understanding how a vector is represented by using the unit orthogonal vectors, we need to clarify few concepts, some basic concepts. So the first one is the magnitude of vector. So as I have told, if a vector is A, the length of that vector in that directed line segment is called the magnitude. As you can see on the screen, this is the vector A starting from this point, ending at this point, which is represented by this symbol, vector A, and the length of this vector, which is starting from this point, ending at this point, this is the magnitude of the vector, which is represented by mod vector A. Okay, so this is about the direction of the vector. This is about the magnitude of the vector. The next thing that we need to know is something called unit vector. So what is a unit vector? Unit vector is basically a vector having a definite direction and magnitude equal to 1. So if we have this vector A, its length or magnitude is the modulus A vector. Now imagine a small vector in the same direction as that of the vector A, but whose length is equal to 1. So if this length is measured, this length will be equal to 1. Okay, so the length of the small vector a cap is equal to 1. Why it is denoted by a cap? A, because it is in the same direction of the vector a, and cap denotes it is an unit vector whose magnitude is 1. That is, the magnitude of this a cap or unit vector is always going to be 1. Okay, so any vector, if it has a definite direction, another vector in the same direction having a magnitude of 1 will be equal to the unit vector in that direction. Now, mathematically, a unit vector can be found out by this formula, which is a vector, which is a total vector A divided by the magnitude of the vector. So if we divide a vector with its magnitude, the thing that is left is basically a unit vector. Okay, now if we just cross multiply, we can alternatively write in this way also. This is a very important concept in understanding vectors, that any vector can be basically written as the magnitude of the vector multiplied by the unit vector in that direction. Again, I am repeating, any vector can be represented by the product of magnitude of that vector and the unit vector in that direction. Okay, so if we have any vector is basically equal to the magnitude. Okay, it will be equal to the magnitude multiplied by the unit vector. Okay, so any vector is magnitude times the unit vector. Unit vector should be in which direction? In which the original vector is. So if unit vector is along x-axis, this vector will also be pointed along x-axis. If unit vector is pointed along y-axis, then this vector will be also pointed along y-axis. Okay, and if it is in some random direction, in some say 45 degree with respect to x-axis, if the unit vector is in that direction, then the original vector will be also in that direction. Okay, so with that concept, let's go to the next concept, which is called the null vector. Null vector is simply, it is a zero vector, which is basically a vector having magnitude 0 and no direction. Now, from where does this concept come? So let us imagine a car which is standing on the road. It is standing still. A car is supposed to have some velocity when it is moving. So as it is standing still, its velocity is 0, but still velocity is a vector. So in that case, velocity of a car which is standing still is a zero vector or a null vector. A vector with zero magnitude and no specified direction. Why no specified direction? Because the car can start moving in either of the direction. It can move forward or it can move backward. So we don't have any definite direction as long as it is standing. Then the next important thing that we need to understand is every vector, as it is a directed line segment, so it has to have a definite starting point and a definite ending point, as you can see on the screen. So if this is the starting point, this is the ending point. Okay, direction of any vector can be defined in terms of that directed line segment. And another thing is that this is basically the symbol of zero vector. Okay, a zero with an arrowhead at the top. Okay, now if we have a zero vector in 3 dimension, if we are dealing with a problem in which a motion is having in 3 dimension basically, then it will be denoted by 0i, 0j, 0k. Okay, now this also has some cap, I cap, j cap, k cap. What are they? We'll see, don't worry. In 2 dimensions, a zero vector can be represented as 0i cap plus 0j cap. Okay, so zero vector is basically can exist in 3 dimension, 2 dimension, or maybe even in 1 dimensions also. Next is unit orthogonal vectors. So we know what is a unit vector. Unit vector is basically a vector of magnitude 1 and directed in a specific direction, in the direction of the original vector. Now, unit orthogonal vectors are also unit vectors. These are basically there are basically 3 unit orthogonal vectors. Each of them are directed along each coordinate axis. Okay, so the first unit orthogonal vector is I cap, which is directed along x-axis. The second unit orthogonal vector is j cap. As you can see, this is I cap, which is directed along x-axis. Okay, the second unit vector is j cap, which is directed along y-axis, and the third is k cap, which is directed along the z-axis. So I cap, j cap, and k cap, these are the 3 vectors, 3 unit orthogonal vectors in physics in the 3 directions x, y and z. Now, as they are unit vectors, so their magnitudes are also going to be 1. So mod I cap is 1, mod j cap is 1 and mod k cap is 1. Now, the important concept that I had told you in the last slide, it was any vector is basically magnitude multiplied by the unit vector in that direction. So if we extend this concept here, as we know a unit vector along the x-axis, if we multiply this unit vector with the magnitude, so if we multiply I cap with some magnitude, we will get a vector in x-axis. Okay. If we multiply some magnitude with j cap, then we will get a vector along y-axis. If we multiply some magnitude with k cap, we will get a vector along z-axis. Okay. So simply by multiplying some scalar with I cap, we will be getting a vector along x-axis. Multiplying a scalar with j cap, we will be getting a vector along y-axis, and multiplying a scalar with k cap, we will be getting a vector along z-axis. The scalars are basically the magnitudes or the lengths of the vector that we are trying to form. So, unit orthogonal vectors are very important because by using this I cap, j cap and k cap, we can define any vector along x-axis, y-axis or z-axis. Okay. So, in these 3 directions, all the vectors can be defined by using I cap, j cap and k cap. Just multiply I cap with a scalar, you will get a vector in x-axis, and similarly for y-axis and z-axis with j cap and k cap respectively. Then the next concept is the parallel shifting of vectors. Now the vectors always have a definite direction, but parallel shifting is allowed. As you can see in this diagram, the first one, I have written 1 here. In this first case, this is the vector which is having a definite direction and a definite length. Now this vector can be basically moved. So if this is the vector we have, now this vector can be moved in space. Okay, as I am showing, it can be moved to here, it can be moved to here, okay, it can be moved to here. So I'm just parallelly moving it. Why I'm parallelly moving? I'm not changing the direction. Okay, this is basically a parallel movement. As you can see on the screen, I'm moving this vector parallelly. Now what would have been a non-parallel movement if I would have rotated this? Okay, this would be a non-parallel movement. As you can see on the screen, this would be a non-parallel, but I am rotating, I'm moving this in the parallel shifting. So basically I'm moving it parallelly to any direction. So parallel shifting of vectors is allowed. It can be moved from one point to the another without changing its direction. If the direction of the vector is kept intact, the inclination of the line is kept intact, it can be moved throughout. There is no change in anything whatsoever. Okay, so the starting point and the ending point of the vector can change if we parallelly shift the vectors. Okay, so with these concepts, now we will see how to define a vector algebraically in 3 dimensions. Okay, so the step 1 will be parallelly shift the vector A to fix the starting point as the origin. Okay, so if you have a vector A in 3 dimension, you have to shift the vector parallelly to a position where one end of this vector, if this is the vector, I have to shift it parallelly until one end of the vector, say at this point, the origin is fixed. Okay, so as you can see in this diagram, let me use blue color. So as you can see in this diagram here, this is the origin here, and this is another end, and this is the vector. Okay, this is the vector that I have drawn, I'm drawing now with the blue color. Okay, this is the vector that I am talking about. One end is at origin, so it was somewhere, parallelly I have shifted it to a place where one end is fixed at the origin. Now step 2, what is step 2? You have to note down the coordinates of the ending points. Okay, you have to note down the coordinates of the ending points. So one end is the origin, which the coordinate is always 0, 0, 0. The other end is the point whose coordinate we have to find out. So let that point be the point A, and its coordinate is denoted by small a, small b, small c. So this is basically the coordinate of the one end point of this vector. Okay, so note it down as capital A, whose coordinate is a, comma b, comma c. Now this vector A is basically composed of three vector components. Okay, this vector A will be basically composed of three vector components: a vector component along x-axis, a vector component along y-axis, and a vector component along z-axis. So our task is to find out these vector components along x-axis, y-axis, and z-axis. Okay, so what are these components? If you see in the diagram, so this is basically the vector component of A along x-axis. Okay, this is vector, sorry, okay, let me use a different color. So let us use say a green color. Okay, so green color, I'll be showing the vector component along x-axis. So this is the vector component of the vector along x-axis. Okay, this is along x-axis. Now what will be the vector component along y-axis? It will be this one. Okay, this line will be the vector component of this vector A along y-axis. Okay, and this one will be the vector component along z-axis. Okay, now interestingly note that all these vector components starts from the origin, from where originally the vector had started. The original vector is shown in blue color here. So originally the vector had started from origin. Its components also starts from the origin. So the originating point of the original vector and the components are going to be same. The components will be always directed along x-axis, y-axis, and z-axis. The original vector will be in any direction. Okay, it is not necessary it has to be in the direction of any vector, in any axis. Okay, so once we have drawn these components, now our task is to find out what is the length of these components. Okay, so we can find out the length of these components. As you can see, if this coordinate is a comma b comma c, then this coordinate here, it has to be a comma 0 comma 0. Okay, if this is a comma, so how this point is reached, this is how we go a distance, this is how we go a distance b, and this is how we come a distance c. Okay, I'm repeating again, the coordinate system, as you can know, if this is the point a comma b comma c, how we reach there? From the origin we draw a straight line until we reach the distance a along x-axis. Okay, then the coordinate is b, so we rise the length b in the vertical direction. Then the length is c, we come forward in the direction of positive z-axis for a distance of c. So this is how we complete and come to this point capital A, one end point of the vector. So using that concept, we can clearly understand that here the the component along x-axis will be, the length will be equal to a. Okay, the component along x-axis, the length will be equal to a. Component along y-axis, the length will be equal to b, and the component along z-axis, the length will be equal to c. So length basically denotes the scalar components. Okay, so the length of this OA is a, length of this OB is small b, and length of this OC is small c. Then what about the vector? Okay, OP vector. So OP vector will be nothing but A multiplied by the unit vector in that direction. Okay, OP vector is basically the length of this OP, which is equal to A, multiplied by unit vector along OP, which is basically I cap. We always have an I cap in that direction of x-axis. We always have a J cap in the direction of y-axis, and we always have a K cap in the direction of z-axis. So similarly, OQ will be basically the length of this line OQ, which is equal to B multiplied by J cap, which is the unit vector in that direction. Similarly, OR vector, which is the vector component along z-axis, it will be C. Okay, this length is equal to C multiplied by the unit vector in that direction K. Okay, so from where we are getting A, B, C? From the coordinates of the end point. Okay, this A will give you the scalar component along x-axis, B the scalar component along y-axis, and C will give you the scalar component along z-axis. Multiply them with I, J, and K cap, you will get the vector components along x, y, and z axis respectively. Now simply add these vector components. So OP vector plus OQ vector plus OR vector, that is AI cap plus BJ cap plus CK cap. That will give you the total vector OA vector, or simply the A vector. So once the endpoint of the vector is known, one endpoint is at origin and the other endpoint is known, its coordinates are known, you can easily write the vector just by using those coordinates. So it will be AI cap plus BJ cap plus CK cap. It will be as simple as that. Okay, you can pause the video here, or if you have understood it, let's go to the numerical, the first numerical of this class. Okay, so let's use a blue color here, say. Okay, so we have been given a vector denoted by 3I cap minus 4j cap plus 5k cap. Then find the following scalar components of vector A along the coordinate axis. Okay, so let's try to draw it first. So the vector is 3I minus 4j plus 5k. So if this is the system, if this is the three-dimensional system, the vector was 3i, sorry, 3i minus 4j plus, I think it was 5k. Okay, that is the vector. So as you can see, 3 minus 4 and 5, these are the things that are here. Okay, so the scalar components are going to be 3 minus 4 and 5. These are going to be the scalar components out here. So now, as we have learned all the concepts that will be required for representation of a vector in 3 dimension, let us see step-by-step method of representing a vector in 3 dimension. So as you can see on the screen, the step 1 will be parallelly shifting the vector to in such a position that one end of the vector is fixed at the origin. So you have to parallelly shift the vector so that one end, preferably the starting end of the vector, is at the origin. Step 2 is note down the coordinates of the endpoint. One of the endpoint is at the origin, that is the starting point. So basically you need to find out the coordinates of the terminating point of the vector. Step 3. Now this vector A can be thought of composed to be 3 vector components. Okay, this total vector A is supposed to be composed of 3 vector components with each vector component along each of the coordinate axes. So the scalar components are like A, B, and C. What was ABC? ABC was the endpoint, the terminating point of the vector. So the scalar components will be ABC along X and Y and Z axis. So now if we multiply the unit vector along that direction, we will get the vector components along the coordinate axis. Okay, and as the unit vector along X axis is I cap, so if you multiply A with I cap, we will be getting basically the vector component of capital A along X axis. As the scalar component along Y axis was B, so if you multiply the unit vector along Y axis, that is J cap, with B, we will get the vector component of the vector capital A along Y axis, which is BJ cap. Similarly, along z-axis, the unit orthogonal vector is k cap. So if you multiply the scalar component with the unit orthogonal vector, we get the vector component. Now simply we just add the vector component along x-axis, vector component along y-axis, and vector component along z-axis, and that together gives us the total vector A. And this is how you can represent a vector in 3 dimension by using unit orthogonal vectors, and in that representation the magnitude as well as the direction both are taken care of. Okay, magnitude, direction, both are taken care of. Now let us see in the diagram the same thing. So you can see this is basically the vector, which was you can think this like a box. Okay, it is a cuboid, not specifically a cube, with all the 3 sides. This is A, this is B, and this is C. Okay, OP is equal to A, OQ is equal to small b, and OR is equal to small c, that is the distance. Now this is the vector which starts from the origin, which is O, at one end, and like this goes to the other end, which is the point of termination of the vector. So the step 1 was we had to parallelly shift the vector Okay, we have to parallelly shift the vector from any position to such a position that it comes to. So if this was the vector, we just parallelly shift it and put it in such a position that one end starts at the origin. Okay, now as one end starts at the origin, we find the coordinates of the other end, which is here. You can see that this is equal to a comma b comma c. That means this small a is basically the distance. Let me show in blue color now. Okay, so this small a is basically the distance from o to this point p. Okay, this length is equal to small a. Similarly, along y-axis, the distance from O to Q, okay, distance from O to Q, this is equal to small b. This distance is small b. Similarly, from O to R, this distance is equal to small c. From where we are getting this ABC? We are getting this from this coordinate, okay? The A, B, and C, and that will be the components along x, y, and z axis. Now, this A, B, and C represents just the length of these three sides, okay? So, they are basically the scalar components. Now, if we multiply them with the vector components, okay? Let's see what happens. So, if we multiply so what are the vector components here basically? So along x-axis, this will be the unit orthogonal vector. Okay, this is basically I cap, unit orthogonal vector along x-axis. Similarly, the unit orthogonal vector along y-axis is j cap, and the unit orthogonal vector along z-axis is basically k cap. Okay, so green colored things are the unit orthogonal vectors. So as we have seen here, we know the length. Okay, we know the length, which is from O to P, that is equals to small a. Multiply this with the unit vector along x-axis, we will get this OP vector, which is this one. This is the vector component of this entire vector. This is the total vector, capital A. Okay, so the vector component of this vector along x-axis is this one, OP, which is AI cap. Similarly, OQ, from O to Q, length is B. Multiply with the unit orthogonal vector, we get bj cap, that is the vector component along y-axis. Similarly, along z-axis, the length is c. Multiply with the unit vector along z-axis, that will give us the vector component along z-axis. So now simply add these three vector components, OP, OQ, and OR vector. So this a vector becomes ultimately equal to, this a vector becomes equal to ai cap plus bj cap plus ck cap. So it will be basically something into I cap plus something into j cap plus something into k cap. Now this A, B, C can be positive, negative, or zero, whatever. Okay, it can be any real number. It can be a fraction, it can be integer, it can be rational, irrational, anything, but it has to be a real number. So A, B, C are any real numbers, positive, negative, whatever. Multiply them with the I cap, j cap, k cap, and add them. That gives us the vector. So this is how basically we represent a vector in 3 dimension by using unit orthogonal vectors. Now let us see a numerical example. So this is the numerical that I have posted on the screen. You can see vector A is represented by 3 I cap plus 4 j cap plus 5 k cap. Now find the following scalar components of vector A along the coordinate axis. So let us first draw this. So this is, I have already ready made this one. This is basically, you can see this is the x-axis, this is the y-axis, and this is the z-axis. Okay. Now this is origin. This is origin, which is 0, 0, 0. Let us mark the end point as capital A. Okay. Let us mark the end point as capital A. So origin's coordinate is always 0, 0. What will be the end point? That will be, we will be getting from here. As you can see, I cap, the component is, with I cap we have the scalar component 3, with j cap the scalar component is 4, and with k cap the scalar component is 5. So these are going to be 3, 4, and 5 are going to be the scalar components along x-axis, y-axis, and z-axis. Okay. So what will be the coordinate of A? Let us first write it down. The coordinate of A will be, it will be basically, okay, let me yeah, this will be basically 3 comma 4 comma 5. Okay, that will be the coordinate of this A. Now what will be the components? Where will be the components? So this will be the first component from this O, until this point. This will be the vector component. Okay, let us mark it as the point P, OP. Similarly, along y-axis, we will have another vector component, which will be, say, it will be OQ. Okay, and this will be OQ. And then there will be another vector component along z-axis, which will be basically, and let us mark this point as R. So this is OR. First, we need to find what is the length. So O to P, the length will be equal to 3. So that is 3 length. O to Q, the length will be 4. And O to Z, the length will be 5. Okay. Now we have unit vectors along them. We know that very well. So unit vector along x-axis is basically I cap. Unit vector along y-axis is basically j cap. And unit vector along z-axis is basically k cap. Okay, now let us return back to the solution. Okay, so what we will write here? So the first one, the first answer is scalar component of vector A along the 3 coordinate axes. So scalar component of vector A along, let us say first along x-axis. The scalar component along x-axis will be is basically 3, along y-axis is 4, and along z-axis is 5. Okay, so these are the scalar components along x, y, and z-axis. Next, you have to find out the vector component. Okay, so vector component is also very simple. Multiply the scalar components with I cap, j cap, k cap. So simply we will write the vector components of vector A along, so first let us write x-axis. Along x-axis is, sorry, along x-axis is 3 I cap. Okay, that will be the vector component along x-axis. Along y-axis is 4 j cap, and along z-axis is 5 k cap. Okay, so that will be the answer for the 2, that is heading number 2. Next is the magnitude of the vector A. Now, what is the magnitude? Magnitude, as I told, is the length of any vector. Okay, so we have here the vector A is represented from this origin to the point A. So we need to find out this length of this line. Okay, O to A. This length we need to find out. That will be the magnitude of the OA vector. So length finding is very simple. When we have in terms of component, it will be square root of this square plus this square plus this square. Now, how we are getting this? It is basically done in the next segment, that is resolution of vectors. In that part, we will be seeing why the magnitude of any vector is got in this way. But first, let us see this magnitude of vector A, that is denoted by mod vector A, which will be square root of the scalar components. We have to square the scalar components and add them. So the scalar components were 3, 4, and 5. So just square it and add it. 3 square plus 4 square plus 5 square. So that is 25 plus 25. So that will be square root of 50, which is again 5 root 2. Okay. So this much you have to write units, because it is not told what unit it is. So you have to write units. So this will be the magnitude of vector A, which is 5 root 2 units. Now how this is coming, let us see in small steps basically. So it is basically coming from Pythagoras theorem. Okay. So this OP, if we have this OP and we have this OQ, this as the right angle triangle, okay, then we can get this diagonal, right? QP, which will be square of this, square of this. So instead of doing that diagonal, if we write say this diagonal, okay, in the 2D plane, Okay, then the result of this diagonal, okay, considered with this one, we will get this ultimate vector. Okay, so it will be basically using Pythagoras theorem two times. We will be coming into the details of that in the next segment. So I'm not getting into the details of this now, but just remember this formula. This has came from the Pythagoras theorem. Okay, so let us see the next part, which is basically a unit vector in the direction of A. So we have to find a unit vector in the direction of A. So let's go to the next page. Okay, so unit vector. So let's see number 4 is a unit vector in the direction of vector A. So unit vector is represented by A cap, which is basically a vector divided by magnitude of that vector. Okay. So this vector here was 3i plus 4j plus 5k. This was the vector. Now divide it with the magnitude which came as 5 root 2. So now you can just divide each of them. So basically it is 3 by 5 root 2 I cap plus, or you can keep like this also, but it's better to separate them. 4 by 5 root 2 j cap, and then we have 5 by 5 root 2, so it is basically 1 by root 2 k cap. So this is the unit vector along vector A. Okay, so magnitude of the vector will divide the vector, and then we will get the unit vector. Okay, so the next question is, if the starting point of the vector is 0, 0, 0, then find the ending point and also draw the vector A using the 3D coordinates. So we have already done this. The end point is 3, 4, 5, and this is the diagram, that is O to A. This is the this from O to A. From O to A, this is basically the diagram of the vector. So let us write down what will be the coordinates of the end point. Okay, so coordinates of the end point of vector A is, that will be 3, 4, 5. Okay, and that completes this numerical. So that was about how to solve questions related to unit vector, magnitudes, and representing a vector in 3 dimension. Now let us see what to do if we have to represent a vector in 2 dimensions. So it is basically a special case of the 3 dimension, in which we are not considering the z-axis. Okay, simply ignore the z-axis in the previous solution. You will get to the concept how to represent a vector in 2 dimension. So in 2 dimension, instead of having 3 coordinates, we will be having just 2 coordinates, x and y. So the steps are quite similar. In step 1, what you have to do is parallelly shift the vector so that the originating end comes to the origin. Okay, so the starting point of the vector is at the origin. So this is the point O, starting point at the origin. Now note down the coordinates of the ending point. So coordinates of the ending point, that will be A comma B. Okay, capital A is the point, it is A comma B. Now we know here we have two axes, so there will be two scalar components and two vector components. So the scalar component along x-axis is basically OP, this length. Okay, OP is the scalar component along x-axis, and the coordinate of that point will be a comma 0. So the length of this OP will be a. Similarly, the scalar component along y-axis will be this length OQ, as you can see on the screen, and this the length of this OQ will be equal to b. Okay. Now the question comes to find the vector components. So to find the vector components, we need the unit orthogonal vectors. So unit orthogonal vector along x-axis will be I cap, and unit orthogonal vector along y-axis will be j cap. So multiply A with I cap, you get the vector component along x-axis. Multiply B with j cap, you get the vector component along y-axis. Okay. Now just add these vector components ai cap plus bj cap, and that will give you the total vector A. Okay, that is how we represent a vector in 2 dimensions, which is simply a special case of 3 dimension where we ignore the z-axis. That is, I think, quite simple if you have understood the 3 dimension thing. Now let us solve a numerical, okay, on this one. So the question is like, if a vector is denoted by 5 I cap minus 12 j cap. So here we are having a negative sign, okay. Then find the following, the scalar component. So it's very similar to the previous problem, but first let us draw this. So you can see one of the component is positive, another component is negative. So what is going to be the end point? So you have to write this vector. Basically, instead of writing this vector using the negative sign, you can write 5 plus of minus 12 times j cap. Okay, it can be 5 I cap plus minus 12 j cap. So what happens? This 5 is basically your scalar component along x-axis. Okay, this 5 is basically the scalar component along x-axis. Okay, and this minus 12 is the scalar component along y-axis. So this is similar to that A, and this is similar to that B, which I have shown you in the previous explanation. So now let us see, we have to draw this point. So the end point of this vector, one of the end point is origin, which is given here. This is the origin here. Another end point is at A, okay, but we don't know the coordinates. The coordinates will be 5 and minus 12. Instead of 5, 12, it will be 5 and minus 12 because there was a minus sign in between. So the coordinates of this one will be 5 comma minus 12, and that's why we see this is in the fourth quadrant instead of in the first quadrant. This is in the fourth quadrant here. So from O to this point, let us name this as the point P. Okay, this length will be equal to 5, and O to this point, which is Q, this distance will be equal to minus 12. Okay, this will be equal to minus 12. Now again the question comes about the unit vectors. So the along x-axis we will be having the unit vector. This will be equal to I cap, and the j cap will be, remember, j cap is always upwards. Okay, it's not downwards. Unit vector is always upwards, okay, in the positive direction. This minus 12 is, the component is negative, but the unit vector is not negative. It is always in the positive y direction, okay. Similarly, I will be always in the right side, that is in the positive x direction. So if we now go and solve it, so let's see what are the things. What will be first? The scalar components. Okay, let us write. First is the scalar components of vector A along, what are the two axes here, basically x axis. Along x axis is 5, and along y axis is minus 12. Okay, that will be a scalar component. So it will be plus 5 and minus 12. Number 2, vector component. So vector component, simply multiply I cap and j cap with the scalar components. So vector components of a vector along x axis is 5 I cap, and along y axis is minus 12 j cap. Okay, so that will be plus 5 I cap and minus 12 j cap. Number 3 is the magnitude. So now you can see, understanding the magnitude would be easier. So if you see here in this one, here O, P, all these things, then this quadrilateral, this O to P, this is equal to 5, as you can see here. Similarly, this is also equal to minus 12, PA. Okay, this length is also minus 12 here. Okay, now this is 5, this is minus 12. What will be the diagonal OA? It will be basically by Pythagoras theorem. We can understand this. We can write here OA square will be basically equal to OP square plus PA square. Okay, OA square will be equals to OP square plus PA square. Now what is OP square? That is 5 square. PA square is minus 12 whole square. So if we just square them and add them, now how to find OA? Take the square root. Okay, if we have to find OA, basically, so if we have to find OA, so we have to use the square root here, this will be the thing, okay, by using Pythagoras theorem. So this OA will be square root of OP squared plus PA squared. Now OP is basically equal to the scalar component of the vector A along x-axis, and PA is equal to this one, okay, the vector component, the scalar component along y-axis. So now let us see the magnitude of vector A, okay. So the magnitude of vector A, which will be basically mod vector A, or simply we can write A also, which will be basically square root of this is 5 square plus minus 12 whole square in bracket. So it will be 169, which is 13. So that will be the 13 units will be the magnitude of this vector. Now next, a unit vector along vector A. Okay, so number 4 will be finding the unit vector along vector A. So that will be A cap, which will be vector A divided by modulus of the vector A. So it was 5 I cap minus 12 j cap divided by 13 was the magnitude. So this is 5 by 13 I cap minus 12 by 13 j cap. That gives us the unit vector along the vector A. Okay, that gives the unit vector along the vector A. Now the last part of the question was, if the starting point is the origin, find out the end point and draw it in 2 dimensions. We have already drawn it. The end point is 5 comma minus 12. Okay, so number 5 will be basically the end point of vector A is at 5 comma minus 12. Okay, and that completes the numerical. Okay, so with that numerical, basically we have come to the end of the segment 3, which was a representation of the vectors. Now we will be seeing the segment 4.